This is AI with Justin. In the previous video of this series, I covered how we can utilize contrastive divergence while training a hopfield network, how adding noise to state transitions makes a hopfield network more resilient to unintended minima, and how adding hidden units increases the potential for a network to model complex patterns. We ended by briefly concluding that a stochastic hopfield network with hidden units can also be called a Boltzmann machine, which is this episode's topic. I'll be covering training challenges that arise from hidden unit addition to a fully connected network, how restricting the Boltzmann machine mitigates these challenges, how the generative nature of a Boltzmann machine enables numerous task capabilities, and lastly, introduce subsequent unsupervised models with deeper latent representations. To begin, I'll quickly recap a high-level overview of a standard Boltzmann machine. The architecture of a Boltzmann machine is a fully connected network with symmetric weights and optional biases. The Boltzmann machine is an energy-based model that evolves to lower energy states via a stochastic Hebbian update rule. The Hebbian update rule is a local learning rule which compares a neuron's value to the output of an activation function which considers the weighted sum of each connected weight and the neuron's current value. If the signs match between the two, the node's value is flipped. Otherwise, the state persists. The rule becomes stochastic when, probabilistically, the value is flipped regardless of the update rule's output. We train the network utilizing contrastive learning, leveraging the energy dynamics of the system. Lastly, each neuron in a Boltzmann machine is either a visible neuron, neurons that contribute to the pattern, or a hidden neuron, neurons that don't contribute to the pattern. Okay, now that we're caught up, let's talk about some challenges of training Boltzmann machines. Without hidden neurons to train our network, all we needed to do for the positive term of the algorithm was to calculate the average of each neuron's value at each position. This worked because every neuron corresponded to a value in the pattern. There was only one desired network state in relation to each pattern. When hidden neurons are added, this is no longer true. There are now multiple accepted network states, each of which contain the desired pattern as a subset. This creates a major issue for the training complexity of Boltzmann machines. Computing the energy minima for every combination of a valid pattern configuration will be intractable. As a result, we need to do our best to approximate each possible pattern by expanding the training data with many randomly generated hidden unit states for each visible unit state. To do this, we will repeatedly generate training batches for both the positive and negative terms and apply gradient optimization. Let's walk through some pseudocode outlining the training algorithm. There will be a clamp phase where the visible neuron values are fixed in place, and an unclamp phase where the visible neuron values are fluid. During the clamp phase, given a training pattern, we'll randomly initialize the hidden neurons and allow the network to stochastically evolve to a minima. This will give us one visible hidden unit pair. Using the same pattern, we'll repeat this process of randomly initializing hidden neurons and evolving to a minima some number of times depending on how closely we decide to approximate each pattern. During the unclamp phase, we'll initialize the network at each pattern with random hidden units, just as we did before, but this time we'll allow the entire network to evolve. Once the number of samples fulfills our batch size, we'll apply an update to the weights utilizing the generated samples. Now we'll repeat this whole process until our network performance has converged or met some performance metric. While this algorithm is eventually effective in approximating the target distribution, it's very costly computationally. And we can make a simple change to the network's architecture which alleviates much of this cost. The change I'm referring to is restricting the network, or transforming it into a bipartite graph. In this graph, hidden neurons make up one layer, visible neurons make up another layer, and no nodes in the same layer share connection. So how does this improve the training process? Whereas in a fully connected Boltzmann machine, there were multiple acceptable network configurations per pattern, we've returned to there only being one optimal network configuration per pattern, as it was before our network included hidden units. For each fixed visible layer state, there is a single hidden layer state that minimizes the energy for the network. This means that our trading process no longer needs to have an inner loop, which iterates many times to get variations of hidden states for each pattern. It also means that instead of having separate positive and negative trading set generation phases, we can actually combine the two into one. Let's look at an overview of the RBMs training algorithm. In its one and only training phase, we initialize the visible units to the pattern and the hidden units randomly. We next apply Gibbs sampling to the network, in which we iterate back and forth between minimizing the energy for either layer. Note that we start by adjusting the hidden neuron values first. This actually gives us the visible hidden value pair for our first term. After continuing and iterating many more steps, the final visible hidden value pair is taken as our second term. By iterating many steps, we've allowed the network as a whole to drift towards an energy valley, as we've referred to in previous videos. So when we maximize the energy for this pair, we raise that valley. So far in this video series, I've talked about what hopfield networks and Boltzmann machines are and how they function, but not so much about what they can be used for. Let's explore that topic a bit. Hopfield nets and Boltzmann machines are generative models, meaning they attempt to model the distribution of the data itself, rather than to solely indicate how likely a label is paired with an instance, as discriminative models do. This characteristic enables a wide array of use cases for each model. As mentioned in previous videos, each model can act as a content-addressable memory system, where incomplete or corrupted patterns can be provided as input to retrieve full patterns. For classification and regression, outputs can be included as part of the training data, forming a joint distribution of input features and perhaps class labels. RBMs are famous for their usage in the Netflix Prize of 2009, where they were applied to the task of collaborative filtering. Essentially, RBMs were trained to estimate the probability that users would enjoy unwatched movies, given the ratings they gave previous movies. Boltzmann machines can also be used in some scenarios to generate new data, which represents the distribution it was trained upon. The invention of the Boltzmann machine in progression to RBM was not just important because it improved the state-of-the-art in statistical modeling, but also because it was the first widely recognized model to emphasize the use of latent representations. Latent features proved to allow the Boltzmann machine to model distributions over visible state vectors that could not be modeled by direct pairwise visible unit interactions. Models like the deep Boltzmann machine, deep belief network, and Helmholtz machine continued this trend of deeper models in unsupervised representation learning, and I'll be exploring them in the next video of this series. If you found this video useful, please give it a like and consider subscribing.